Hello YouTube viewers, welcome to my channel Science to Technology. In today's show, Rocket Monday, we're going to talk about 3D printing rocket engine. So what the hell is going on in this? So let's dive deep into it. Now first, what exactly is the problem with rocket engine, so to say? Well, it's one of the most complex engine. Like basically, when we have to say that something is hard, we say it's like rocket science because it is ludicrously difficult. Why? Well, it has temperature extreme. Like for example, your stove, it could literally go from ambient temperature to ludicrously hot of 400 degrees Celsius. Here, we start at cryogenic temperature, meaning if you are dealing with liquid hydrogen, your cold end temperature is minus 253 degrees Celsius. And how hot is hot? Yeah, that puppy can go up to 3200 degrees Celsius at the core. Basically, you cannot even have it touching any material. It has to be in void. Basically, you have to encapsulate it. So fundamentally, that's the core issue, that it has ludicrously long temperature range. And then it also has massive flow rate, meaning this puppy consumes fluid like there is no tomorrow. Meaning you can have a best pumps that can drain reverse dry. This is like bruh, don't waste my time. Like it can consume tons of fluid per second. So it's bonkersly. And on top of that, not only liquid, it converts it into gas and then flows it out. To give you a context, if you have that kind of flow, it can etch through materials. Basically, with a stone flowing that much gas, it will erode. So fundamentally, it's a bonkersly large amount of flow rate. And then because we are talking about combustion is not a smooth event. It's not like everything is nice. It has some noise to it. Now that noise in this sort of scenario becomes a very bad noise. It creates shocks, vibration, pogo oscillation, this and that. Oh, and let's not even forget about fighting against the atmosphere. Again, atmosphere will have different pockets, so that will create vibrations. And not to mention max Q, it puts extra amount of oomph to you. So you have to be damn sure that you can handle all of this. Basically shocks, vibration, environment, you have to be like, I do not care. And so far, not that difficult actually. Realistically speaking, all these things, basically something that can handle this sort of temperature, no problem. Something that can handle vibration, environment, all that, no problem. Giant flow rates, no problem. Yeah, make them light, impossible. So that's the whole problem. Like making a rocket engine, any Tom, Dick and Harry can do. Make a rocket engine that is light enough, basically it actually goes to space. Now you're talking. Like at that point in time, you will understand why the heck it takes upwards of 10 years to make one. So fundamentally, basically, if you reach that point where it's like, okay, I have to make something that, it's basically a dragon's breath. How the heck I make sure I do that with as light as possible? It is difficult. Like fundamentally, it's a complex problem to solve, to have all of this while being as lightweight as possible. So how do we used to do it in the past? Well, first you have to understand the most annoying part, basically the tedious part, the tedious maximus is injector plate. And injector plate is complex AF, meaning fluid simulations are done for this puppy. Basically, how the heck you're gonna have liquid going there, and is it gonna convert into gas, or are you flowing gas directly? How are you basically having fluid streams making love to each other and becoming atomized? If it's not atomized, it's not stable. How do you atomize it properly? All of those things have to go into the calculations of these holes, and these holes are so tedious that somebody will actually be like this, and it's like drilling one by one. Like each of these plate takes time, like seriously large amount of time. Like you're just like, okay, what are you doing? Injector plate. 1 month later, what are you doing? Injector plate. 1 year later, yeah, I'm about to finish the injector plate. Not even joking. Like this, even with CNC machine, modern CNC machine, these things are still goddamn tedious. Basically, you'll have whole thing and then injector plate. Just put it, forget about it. It's gonna take its sweet time. So it's very idiotically difficult. And that was, again, we figured it out. Once we figured it out, once we started to make jigs for it, once we have rudimentary automations, we're good with that. Now we come to the tedious part. Basically, how the heck you deal with this thing. So this is what we call regenerative cooling, because that's the only way where you can have high enough temperature without basically kaputting the engine. You can have graphite on the other end, but it will ablate away. So it will give you a fixed lifespan. Again, suitable for use and throw, but not desirable, and not to mention it does not have that much performance. So for that reason, you generally want to have regenerative cooling that gives you the oomph needed. But how the heck you cool that much? You have to have bonkersly large amount of surface area with thin metal. That will be very clear. The metal has to be thin, otherwise the heat will not conduct fast enough through it. Because again, even if you describe metal as a conductor, if you have a thickness of metal, heat from this side to this side takes time. And if it takes too longer, basically, let's say it's very thick, problem is by the time it heats reach here, this part will start to melt. So you have to make it as thin, but again, you are talking about a lot of flow going through it. So it has to be strong enough to handle that, but thin enough to conduct very quickly. You must have heard about this experiment. You can boil water on paper. You must have like make a small boat out of basically paper, put it, boil it, because again, if paper is thin enough, heat can conduct very quickly. So same rule applies here. You do not want to make these pipes fat. You're like, okay, this can handle it. No. You want it to be as thin as possible. I've linked an ancient video down below, basically how they used to do it for R10 engine back in the Apollo era. And again, you have to, these are pipes. You bend the pipe. We good. We got this. How the heck you connect pipes? They use silver. Not even joking, actual silver, to braze each other to them. So basically that created the nozzle, so to say. Sometimes you will have a copper clad, and then on top of it you will braze pipes. Sometimes you will have raw pipes, depending on design and all that. So that's how we started. But then we realized, like, basically this was Saturn V era. By the time we reached to space shuttle, it's like, yeah, this is good, but we need something more oomph. So we needed something like that. Basically for combustion chamber itself, not the nozzle pipes are good. Chamber itself, you needed even more flux throughput. Basically just like leach the heat away, otherwise it will kaput itself. So how the heck you leach heat away from there? Well, you need lot of tiny tubes. That cannot be done. Like, that was not possible. So how did they do it? They figured out they're gonna make a sleeve, copper sleeve, and they're gonna etch channels to it, either by CNC, EDM, whatever have you. You etch into it. Okay, that only gives you half of the system. So then you electroplate the hell out of it. You basically, layer by layer, you build an electroplating layer on top of it, and ta-da, you have it. Does it work? That's how majority of space shuttle engines worked. Now we don't do that anymore. That was cool trick for 1970s, but now we have magic technology known as ISO, hot isostatic press. Basically, you take these two parts, you put it in a chamber, and you heat that puppy up. Like, not as hot as melting, but just below melting, or just below thermal softening, depending on the metal alloy. And then you put pressure, and I mean bonkersly large amount of pressure. Now, of course, you have to use nice gas for it, generally argon, and then you pressurize the hell out of it. And I do not mean in PSI, I mean hundreds of bar, like bonkers amount of pressure, bonkers amount of heat, and then it welds. It fuses, basically on a molecular level, it fuses. So that gives you the perfect welding. So these are the core technology. Basically, if you want to make a rocket engine, these things you have to understand. Basically, how the heck you make this sort of tubing, and how the heck you get the injector plate. Once you have these things, turbo pump is like a different beast, but these are the annoying parts. Turbo pump is like, yeah, it's a turbo pump. These things are like, nah, we are bespoke parts. So that's how we started. So let's understand 3D printing. Now, one thing you have to understand, 3D printing is old technology, as in like 1980s kind of technology, but it had patents. Certain companies, keep forgetting the name, it's from S. They had the patents. Now, thankfully, every country has the wisdom that patents is granted, because again, if some inventor did came up with it, they should be able to make money of it. Awesome, GG. And they had enough wisdom is that it should not create a monopoly, so 20-year time frame was chosen. Is that for 20 years, you can do whatever you want. If somebody clones it, we fire missile at him. Cool. But after 20 years, you lose that right. Thankfully, all the patents on fuse deposition modeling fried in 2009. Now, why that is a big deal? You have to understand. Company was smart. Company made a patent, but again, company is small. As in, it is not even 1,000 top scholars working there. Not even 1,000. Not let alone 10,000. Let alone 1 million. But the moment patent expire, this movement started. Rip-rap movement. Instantaneously, hundreds of colleges started to work on it. Nerds all around the world started to work on it. So growth from basically 1990 to 2010 is negligible. Growth from 2010 to 2020, it's mind-bogglingly huge. Why? So much brain power is added into it. New companies come into market, slicer software becomes awesome. Brick by brick, day by day, thousands of compute horsepower is poured into it, and now we have printers, we don't even think about it. All that was not possible if only one company was working on it. Now, sometimes again, companies are smart. When they make patent like this, they actually sell the patent to other companies. Like, yeah, we made cool stuff, but cool, it won't be cool if we only are the one dealing with it. We'll try to create monopoly, it will not work. Like CDs, Blu-ray, every company was smart enough where it's like, hey, we made it, it's awesome, but other people have to use it. So CDs, patent was open for other licensing, but again, at least open further. That's how it works. But 3D companies were like, nah, I'm gonna keep it and we're gonna disappear. I'm not even joking, they had a patent for somehow a heated chamber. That's an oven. How the heck you have a patent on that? But thankfully that has expired. That's why we have heated chamber. So you have to understand, after 2009, the brain power available on 3D printer just went quantum boom. It's like kaboom. And same happened with metal 3D printer. We also had the technology of metal 3D printing in 1990s. That was like a common thing that we could do. Just people did not knew about it. Why? It was so expensive. Lockheed Martin looked at it as like, bruh, it's expensive, man. Not even joking. And that's why it was not popular. Company was like, hey, but we patent it. It's just like, give license. Make money off license. Don't capitalize on it on yourself. You are not that good. And thankfully that patent also expired in 2010s, and voila, metal 3D printing started to reach the market again. So mass adoption already happened. Like jet engine companies jumped into it so goddamn quickly. It's like you were waiting for patent to expire. It was like Rolls-Royce is like, boom, patent expired, boom, done. All the new engines have turbine blades that are made in 3D printers. I'm like, damn, you guys were waiting for that patent to expire. So that happened. And again, what's the benefit of it? More and more people got into it. Heck, at this point in time, there are YouTubers who are trying to make laser fuse deposition in their house. Not even joking. So, and again, some people are trying with MIG welding, some try this and that. Lot of awesome work is happening. And again, you need brain power. No matter how smart someone is, single individual is not that valuable. If you have hundreds and thousands and millions of individual, development would be quantum high speed. So that happened in 3D printer. So by 2010, things started to go. So what's the reality of it? Well, things started to go, but people realized very early on that 3D printing for rocket industry is hard. So why is that? Well, generally there are two variables. If you go like this, it does not give you a lot of resolution, but it gives you durability. And if you want like nice, intricate flow channels, yeah, those puppies are not very, what we call robust. Basically, either you can have resolution or durability, basically how laser pattern is working. Fundamentally, we have not figured out a technology where all of the things can be done without any penalty. It's early stage. It's a barely 10 years old technology. So it needs some more time to cook. So the first big boy jump was 2013. SpaceX started to 3D print main oxidizer valve. Now that's a very big deal simply because before that, again, jet engine companies, they were waiting. The moment 3D printers are like, boom, they just yeeted out of there. But rockets company were very hesitant, but thankfully SpaceX did try it, and main oxidizer valve became the first dark horse, so to say, and people were like, whoa, 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 you can do that? So, and then we have 2016, Rocket Lab makes literally the whole engine block, and the reason why he can do that is because there is no turbo pump, it's electrical turbo pump, so it was doable for them. They did it. And by 2023, we have this puppy. They went a bit extra on it. Like they went so much extra. It's like, okay, 85% of the rocket's mass is 3D printed. It's like, yeah, that's a bit much. Thankfully, they have scaled it back. It's like, yeah, tanks and like tube does not need to be 3D printed. You can 3D print it. It's unnecessary. So they are scaling back. Again, engines and all the complex things that still would be 3D printed. But the tank is like, yeah, it looks cool. It's just that overkill. So they went that. And even in India, Agnikul successfully made monolithic engine block, meaning when you're comparing this engine block, it has multiple parts. This puppy, take out the printer board, shake the powder, ta-da! So that happened. Now the reason why they can do it simply because it was a monolithic system, meaning, pressure fed engine, not a turbo fed engine, pressure fed engine. So things are moving. It's not reached the like control C, control P, but things are moving. So what can we expect in the future? Well, reality is right now the thing that no company will touch is turbo pump's rotor, turbo pump assembly, turbo pump fluid channels, everything done, take it and go home. The moment you talk about I want to make the rotating shaft, yeah, like no, don't even bother about it. Don't even try to think it. It is the hardest thing to do. And again, those puppies can easily go from 20 megawatt to 100 megawatt. So you are talking about something that is spinning bonkersly fast, like 20,000 RPM to 100,000 RPM. They're almost at the same speed as turbocharger speeds. So you do have to understand that thing. People are like, yeah, let's forge that puppy. Let's have like solid, robust, nuclear bomb proof kind of design. So that's why we do not touch that part. Everything else, we got it. Turbo shaft, it's like, yeah, no. Turbo shaft is like, no. And why is that problem? The problem is 3D printing fundamentally creates a lot of void. So when NASA is testing it, and if you look into electron microscope, you will see powder that is being melted. So fundamentally, it's not as robust as forged part. Forged part would be got here, and second would be like a liquid casting. So you have liquid metal pouring, gravity is like shaking it down, and you shake it, gases moves up and all that. So that gives you a very dense part. 3D printing, it's good. It's good. We are using it, but it's not that good. So thankfully, we have a technology to bypass that problem, which we use for normal rockets anyway. It's Haas isotropic pressing, meaning if you take a 3D printed metal part, it's good enough. But if you use it, it's useless. So how do we make useless or to like barely works to like a rocket grade? Well, we cook that puppy. So how do you cook it? You put it in a chamber. You heat that chamber as hot as possible and you pressurize it as high as possible. It does shrink the part a little bit in some designs, and some designs are depending on the alloy, but it removes void internally, meaning there won't be any void. So it makes the part denser, and at that point in time, it's actually usable. And that's what every jet engine company does for their turbine blades. So they have a lot of nice, intricate, basically cooling vents. Yes, turbine blades have cooling vents. So from a compressor stage, there is a hollow shaft that dumps air into the turbine blade. Turbine blade has an air curtain. That's how they are not melting from the furnace, that is jet engine fuel. So that furnace is putting there, but the air curtain is like, I got you, fam. So how the heck they made it? Well, 3D printed. But again, if you 3D print it and spin it as fast as those things, yeah, it will shatter. So they take it, they cook it. Once you cook it, now it's like, I got this. So you have to still understand that part. Take the 3D metal printed part and cook it. Once you cook it, then you can do whatever you want to do. But again, cooking is not that easy. There are only few countries that can do really high grade hot isotropic press. Like, it's not that cheap, because again, that much pressure, that much heat, it's a boom device. So it's very difficult. And as of now, the most bonkers experience with 3D printing is Raptor version 3. And again, I do not know how they are doing it, what sort of geometry they are doing it. Even the electronics are inside. I'm not joking, electronics are inside the damn rocket engine. So they did that. Now, let that be very clear. Can anybody do this? More or less nowadays, yes. It's just that you still can't touch a rotor. Like injector plate, got it. Turbo pump geometry outside the casing and all that, got it. Nozzle, got it. Combustion chamber, got it. Turbo shaft, no. And that's why you see a lot of bolts in that area. It still needs to be opened up so you can put the turbine. And again, look into how they are dealing with the bearings. So we can make rocket engines quite good nowadays. It's just that turbo pump, the moment you are talking about turbo pump, so rotor is like, that's still, I think people might be like, dude, it's a simple shaft, use a lathe, don't try to do too much advanced thing, just chill with it. So future is looking very bright with it. But again, let that be very clear. Do not just say 3D print it, go home. No, we are not there yet. Some people are claiming that with electron beam welding, we might be able to reach that kind of strength where you just take the part and use it. But right now, current topology is make the part, test it and all that, and then ISO hot press it. Without that, and again, that process is not cheap. And so you have to be kind of loaded with money to try that. But future is very bright. So we can see a future where people can make very awesome 3D printed stuff, and things gonna be interesting. So this was my presentation on basically 3D printed rocket engines. Hopefully you have liked it, learned from it. In that case, please hit the like button, share it amongst your friends. That will help me a lot. If you didn't like it, didn't enjoy it, I urge you to press dislike, press it twice to show me extra disappointment. Please leave a comment because I do try to reply to all of them. Subscribe, press the bell icon if you're free, and as always, thanks for watching.